In this session, let me learn about how to design a synchronous down counter. So in last session, we learned about synchronous up counter designing. The same procedural step we are going to follow to design your down counter sequence. So now let me find your number of flip-flops. Thereafter, we choose your type of flip-flop. Then we'll draw the state diagram. Upon drawing the state diagram, we will write the excitation table. Then we will find your each excitation inputs minimal expression. After that, we are going to draw the logical diagram of your down counter. Now let me choose your first. So they have given the question which is 2-bit synchronous down counter designing using your toggle flip-flop. So let me find number of flip-flops to be used. As it is given in the directly they have given in the question itself 2-bit. So here I need to use 2 flip-flop because since your each flip-flop can hold 1 bit of data, so you have to use 2 flip-flops. If you take 2 flip-flops, the number of states available are 4 states, which are initial state is 0, 0, next 1, 1, 1, 0, as well as your 0, 1. Choose the type of flip-flop, which are your toggle flip-flop. Then we are going to draw the state diagram of your counter. So initial state is 0, 0. So next state upon giving the clock, it will be 1, 1. So 1 after 1, 1. So the next state will be 1 0, which is 2. So when you clear your counter, so you can have your initial state is a 0 state, so which is 0 0. Thereafter, so upon giving the clock signal, we can obtain your counter state is equal to decremented by 1. So first clock pulse initial state is 0. First clock pulse we obtain 1 1. Next clock pulse, second clock pulse, you obtain your next state is 1 0. Third clock pulse, you obtain your 0 1, and your fourth clock pulse, you obtain your initial state, which is again the 0 0 state. So hence, so upon this state sequence, let me draw the state diagram. So I have taken each state with a one circle, state 0, state 1, state 2, as well as your state 3. So first S0 is the initial state of your counter is started with 0. Next, upon giving the first clock pulse, you obtain your 1 1. Second clock pulse, you obtain your 1 0, which is 1 is decremented from your previous state, 1 1 minus 1, 3 minus 1, which is 2. Next 2 minus 1, which is translated as your S3, as I counted here S0. So I have total 4 states. So after 0 1, so next state will be your initial state, which is your 0 0. So 1 minus 1, which we get is 0. So next, so upon drawing the state diagram based on this state transition, so we are going to draw the excitation table using your excitation table of your T flip-flop. Now in that excitation table of your counter, so let me write your present state, next state in the flip-flop inputs required. So QB, QA are the present states, QB plus 1, QA plus 1 are the next states of your each flip-flop, and TB and TA are the excitation inputs required in order to obtain the state transition. So using the excitation table of your T flip-flop, let me find the what are the excitation inputs required on this counter down sequence. Now, so 0 to 0, toggle input is 0, no state change here, same state. So toggle input is 0. 0 to 1, toggle input is 1, and only the state will be toggled from 0 to 1. 1 to 0, it causes the toggle input when it is 1, so it causes state transition is a complementary state from 1 to 0. 1 to 1, so there is no toggling, same state is continued, hence that toggle input is 0 in your excitation table. So based on this transition 0 to 0, the input 0, 0 to 1, 1, 1 to 0, 1, 1 to 1 is 0. So you can write the excitation inputs required on this by comparing QB, QB plus 1. So 0 present state, next state is QB plus 1. So 0 to 1, so TB value is 1. So as 0, 0 is toggled to 1. Next 0 to 0, so QB is 0 and QB plus 1 is 0. So hence here the TB value is 0, and 1 to 0, so we wrote it as a TB value is toggled, so your next state is toggled, hence TB value is equal to 1. 1 to 1, so no toggling occurred, so 1 is your QB, next state is also 1, so T value is 0. So now based on your state diagram, we have drawn the present state and next state. So initial state is 0 0, next state is 1 1. So if your initial state is 0 1, next state is decremented by 1, so which is 0 0. Initial state is 2, next state is decremented by 1 is 1, 2 minus 1 is 1, so binary equivalent is 0 1. So if my initial state is, present state is 1 1, next state must be 1 0, so which will give you the down sequence. So upon writing this, then we compare your QB plus, and we will write your TA. So now we will compare your TA and QA and QA plus 1, and then we write your TA value. So our input of your toggle flip-flop A. So 0 to 1. So 0 is the present state, next state is 1. So toggle, so TA input is 1. Next 1 to 0 here. So again toggled, so present state is 1, next state is 0. So toggle input of TA is 1. So 0 to 1 in this state of your clock pulse. So hence here, so TA input is 1. So 1 to 0, TA, QA is 1, QA plus 1 is 0. So here also the next state is toggle, so TA input is 1. So now let me write your standard SOP function in terms of your present state TA in terms of your as a function of your QA QB is equal to sigma m of, so you're having all the midterms, so 0 1 2 3 4, so 3. So like here all the midterms are logical ones. So if I draw the midterms, it can form a square and it will give you the logical output function, which is equal to, so it's a two variable function. In that two variable function, all the midterm functional values are logical one, and the minimal expression is equal to logical. Where if you write for TB, so only we have two midterms are available on your 0 as well as on your 2. So the remaining two midterms are a logical 0, so we are not including that in your standard SOP function. So now here let me derive those. So TB is equal to, so it is marked on this 0 as well as your 2. So 1 comma TB is equal to 0 comma 2. So TB value is 1 for 0 as well as for 2. So we wrote that or map your function 0 comma 2, and TA is, we have all four midterms, so we map your function, and if all midterms are 1 in a two variable schema, that function value is equal to logical. The TB is equal to QA bar. So QB is different for these two midterms, only QA is the common variable for the two midterms given, and the QA value is assigned with 0, hence in your product term it is represented with the complement QA bar. Now upon obtaining this minimal expressions of your each excitation input, then you are going to take your two flip-flops of toggle flip-flops, and which are operated with a common clock signal. Then here we are going to take that common clock signal. Upon finding that TA is connected with logical and TB is connected with your QA bar of your first flip-flop A, which is the least significant bit, and B is your most significant bit. You can obtain your design of your down counter. So now for the first clockwise, so QA will, for every clock edge or the trailing edge of your each clockwise, state of your QA is toggled from 0 to 1 or 1 to 0, since the toggle input is 1. So hence, so QA output, the first flip-flop or the least significant flip-flop output will be toggled for every trailing edge of your clock. So hence here we denoted that. So initially QA value is reset as well as QB value also on a reset state. So both will give you the 0 0 state or the initial state before you apply your first clock pulse. So next, upon giving the clock pulse, so trailing edge, so negative going edge, so your state of your QA is moved from 0 to the logical 1 state as toggle input is 1. Next, upon having the second clock pulse, so present state is 1, now it will toggle to the 0 state. So now upon having the third clock pulse, present state of your QA is 0, now it will toggle to the logical 1 state. So for every trailing edge of your each clock pulse, your QA output will toggle from 0 to 1, 1 to 0, again 0 to 1, like that it will be toggled. So for every clock edge of your input which is given on your first flip-flop. the same manner. So your output of your second flip-flop is toggled based on your input which you apply on your toggle flip-flop of second flip-flop, which comes out from your present state, which is coming as a input to the toggle flip-flop, second flip-flop, which is the first flip-flop output. So QA bar is connected on your second flip-flop as the input now. So initially, what will be the present state on your second flip-flop is logical 1. On your trailing edge of your first clockwise edge, since QA bar is 1, so your flip-flop second flip-flop output will move from 0 to logical 1, and this state is continued till you have your third clockwise. On your second clockwise, since our QA is 1 and QA bar is 0, so this 0 is applied as your toggle input, which is equal to TB. So now when TB is 0, next say on your second clock trailing edge, so it has to continue the previous state as your next state. So hence previous state is logical 1 on your second flip-flop, so that is continued till you get your third clockwise. On your third trailing edge, so since our QA bar is logical 1, so TB is equal to logic 1. So present state of your second flip-flop is logic 1. Now it is toggled to the 0 state. So hence, so on your fourth clock pulse, so your QA bar is 0. So TB is equal to 0. So when TB is 0, so on your fourth clock pulse, so next state must be the previous state since of the toggle input is 0. So when toggle input is 1, then only your second flip-flop will toggle. So since my previous state of your first flip-flop is 0, hence it has to continue the previous state as your next state. So now my present state is 0, next state of that flip-flop on your fifth clock pulse is 0. But when you are coming with your fifth clock pulse, so on your second flip-flop, QA bar is logical 1. So now it becomes TB is equal to 1. So when it is 1, so your present state, now it will be toggled to the logical 1 state because of this TB input. Now, upon having these all the waves on your outputs of your each flip-flop, the first clock pulse, so initially your state of the flip-flop is 0, 0. At your trailing edge, your QA is moved to the logical 1, QB is also 1. On your third clock edge, so your QB value is 0 and your QB value is logic 1, QA value is 1, 0. Next, on your fourth clock edge, so QB as well as your QA both will give you the 0 outputs. So now when you observe here the state transition, upon giving the first clock pulse, it will shift it to 0, 0 with your first state, and your maximum count we will get as your first clock pulse. Next, on your second clock pulse, the state is decremented by 1, so hence 3 minus 1 you get as a 2. Next, on your third clock pulse, you have your 1. On your fourth clock pulse, it comes back to its initial state. So after every clock pulse, it will give you the down sequence, hence it comes under your down counter. So this is about our today's session, designing a down counter using toggle flip-flop. In your next session, let me design a 3-bit up counter as well as your down counter.